All right, recording is rolling. It is Monday, April 1st. Welcome back from spring break. All right, so we're gonna take a few days to do electricity. Well, my honors classes, we're gonna take a couple of weeks, but my AP classes, we're gonna take just a few days, and for a few reasons. One thing is electricity and electric circuits, right? These topics we're going to be talking about next few days that used to be on the AP exam until the pandemic, and then they bumped the topic a couple of right? This is, I think, good for you to know. A lot of you guys, this might be the only chance you get to learn about circuits and navigating electric circuits. It's a little bit different thought process than anything else we've done so far in this class. But some of you guys will maybe go to college and have to learn circuits. And then if you've seen it for, I remember back in high school, we did that for a few days, and that was really helpful just to have that intro. Also, a lot of the concepts you guys see related to electricity and electric circuits are there are analogous applications to traffic flow. If you're a traffic engineer, want to design some road system in the city, or you have like a pipe network, or you're pumping water all over to different buildings, right? But there's a pipe buried under the ground that's pumping into the school, right? Turn on the faucet. All right, so you guys have this page of thumbnail notes was already on your desk when you walked in. Right, so you guys got this. Go ahead and keep this. Right, and then like I said, for my AP classes, we're just going to take a few days. I'll give you guys a crash course on electricity and electric circuits, and then then we'll go back to doing AP review type stuff. Right. I want to mention too, just a heads up, on Wednesday there's going to be a little bit wacky schedule. You guys see the schedule here? Right. Now there are no periods labeled because we're going to reuse this. You guys know the last quarter school there's all kind of crazy testing going on, so this is going to show up a few times. They're just going to cycle around the periods. Right. But Wednesday, so Wednesday there's a testing going on for 9th and 10th grade, right? 9th and 10th grade, right? There might be a couple of 10th graders in here, but most of you guys not so much going to apply to. But you will go to your homeroom, right? It's going to be the first 2.5 hours on Wednesday, okay? So if you're 11th or 12th grade, just go ahead and go to your homeroom class for first 2.5 hours, and I'll have like a half-hour class after that. Okay, all right, guys, got this. All right, questions so far? Forget rolling on electricity stuff. Yeah, so that one. There you go. All right. All right, so I got this question about these two guys painting. I need to make this one a poster too. I don't know, I haven't yet, right? But and this will the math behind answering this question will relate to some stuff you guys can see later today. Right? And so we got Alan. He could paint this whole fence. It would take him 3 hours all by himself. Bob could do the same job in 4 hours. But they're going to team up. They're going to make a two-man team. How long is it going to take them to paint that fence? Who knows? What's the answer to that question? Yeah, what you got? You go 1.7 hours. Yeah, 1.7. Right. I know. I didn't want to change. Just kind of side thought here is if you did not know how to solve this, then you might be able to quickly get some boundary conditions, right? Like there are a whole bunch of problems in math that are unsolved. Like there are people with PhDs in math that like can't solve certain math problems. Right? What they can do is they can at least set up proofs to narrow it down to like some window. So, well, the answer is between 11 billion and 12 billion. And we know that because blah, 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 right? Even if they don't have the exact answer. How about this? What if it was two Allens? What was Alan and Alan? So 3 hours and 3 hours. Alan and Alan both. Right? How long would it take together to paint a fence? 1.5 hours, right? What if it's Bob and Bob along together? 2 hours, right? Because half of 4 would be 2, right? Okay, so if it's an Alan and Bob, well, it's got to be somewhere between those two, right? An hour and a half, 2 hours, right? And it has to do with the rate at which they can work, and they're working in conjunction with each other. I'm going to skip straight to the math solution, right? It goes like this. Well, this is one way to do it. You can say 1 over the total time, and we're solving for the total time, right, is equal to 1 over Alan's time plus 1 over Bob's time, right? Okay. So let's run the numbers then, right? Because Steve was saying the answer should be like 1.7 hours, right? I think it sounds right. Okay, let's check this out. So 1 over the total time is 1 over, okay, Alan could be 3 hours. I'll just drop the unit, leave 3. You guys get the idea, right? Okay. Bob was like 4 hours, so 1 over Bob is like 1 over 4. Okay. Ooh, guys, what's the common denominator? 3 and 4? 12, right? So I kind of multiply by 4 on 4, multiply by 3 on 3, right? They'll give you what, 7 on 12, I think, 7 on 12. So 1 over the total is 7 on 12, right? So can you, to get the total, just reciprocal, right? So that's 12 over 7. If I restore the unit, it should be hours at this point, right? And yeah, that works out to like about 1.7 hours. There you go. Takes. Okay. Okay. You see that? All right. Now, how about this? If you do so many pairs of teams of people, right? By the way, the math application of this is going to be called resistors in parallel, right? Resistors in parallel, same math we're going to see. Right? If you work with so many teams, you can kind of take a shortcut here and say, well, we're going to do this whole common denominator thing, blah, 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 right? And what it ends up being at the end of the day is, you guys see 12 and 7 is kind of like product over sum. You guys see that? Right? That's as long as you have 2 people painting the fence. So if 2, or I should say, if there's only 2, so we're just focused on 2 people painting the fence. Right, then the total time, so T for total time is product over sum. So Alan times Bob over Alan plus Bob, but that's kind of what we just did, right? Just kind of shortcuts to it, right? Again, it's 1.71 hours about. Okay, right, guys get that? Right. How about this? Thinking ahead another step with these 2 guys painting the fence, right? What if they get a third friend? What if we bring in Carl? Right? Can I do +1 over Carl? You guys think? Right, and then so it could do 1 over Alan plus 1 over Bob plus 1 over Carl. Right? Can I keep on? What if they keep adding friends? Can I do +1 over Derek, +1 over Eric, +1 over Barrett? Just keep going, right? Keep down 1 over Garrett. Right. But right, if I do the product over sum method, can I keep chaining it? Can I throw in Carl as part of the product over sum? No, that didn't quite work. So if I bring in Carl or any other friends, Derek, Eric, and Barrett, I got to either keep chaining it with the fractions like this, right? Or what you can do is you can do 2 at a time. So you can do Alan and Bob and then write that number down, 1.71. And then you can bring in Carl with, okay, these 2 guys together, and then Carl, and then actually it would work product over sum. You could do that way too. Okay. Right. So you guys get these guys paint the fence. Okay. Again, this is going to show up when you guys see resistors in parallel. You guys see a little bit later today. Okay. It's the same math. Same math. Okay. All right. So let's look at electricity. Okay. So you guys got, of course, this thumbnail notes you guys got. We're gonna do as many as I can today. So most of them. Okay. And so variables. Do you guys remember way back in August, I told you guys that there's basically 6 or 7 things that people know fundamentally how to measure, right? And there might be other things in the universe that we just have no idea, like how to measure, possibly, right? But really only 3 of these units we cycled over and over for the entirety of fall semester. If you guys remember, it was mass in kilograms, length in meters, and time in seconds. That was it, right? You take those 3 ingredients, you can make force units and pressure units and momentum units and energy units and torque, right? All those just some combination of kilograms, meters, and seconds, right? All right, so when we get to electricity, I'm going to have to introduce something that's none of those, right? Right. I have to either a charge or electric current, depending on your perspective and what textbook you open, right? Right. So I'm going to start with a charge, right? So remember, there's a variable and there's an attached unit, right? So how charged is an electron? How charged, like some electric charge, you can quantify in coulombs. I'll do an example here with a balloon. Right? So there's lots of protons and electrons in this room, but everything kind of neutralizes out, right? But if you take a latex balloon, rub it against your hair, right? Well, now there's going to be a transfer of electrons from my hair onto the latex surface of the balloon. So now my hair is like positively charged and the balloon's like negatively charged. Right? See if I can, right? And I can quantify how charged is the balloon in some number of coulombs, something like that, right? See if I can stick this to the wall. This works. All right, it's working. Right. So sometimes it works, and there it is. Right. So stick the balloon to the wall. So it's just some kind of electrostatic force pulling, right? Something like that. Right. So I can quantify how charged is the balloon in coulombs. Now, if you set that charge on a wire and get it flowing at some rate, like coulombs per second, right? That's electric current. Or so electric current, the variable is I. So just go with it. Right. So capital I, when you're going to see this loss today. Capital I, think electric current. We're going to quantify how many amps is that, or how many amperes, how many amps. What is 1 amp? It's 1 coulomb per second, flowing on a wire. Okay. Okay. Right now, why would electricity ever flow? Like if I have a charged up balloon, maybe you could touch it and it'll shock real fast or something, right? But well, what if you have like now if you want some kind of like electric circuit, maybe some kind of battery to for electricity to have some kind of impetus to flow, something like that, right? You need a potential difference, right? Potential difference is kind of the fancy physics word for voltage, right? Potential difference, voltage, synonymous, right? So these are the characters you see for it. We're going to quantify this in volts, right? Let's say you pop this AA battery in some appliance. Who can tell me? I bet some of you guys know. How many volts is a AA battery? How many volts? 1.5. Maybe zoom in where you guys can see it. Well, if you're in class, this wasn't blurry. Yeah, there you go. 1.5 volts. Right. That's true for AAAs, C cells, D cells. They're all 1.5 volts. Right. So between the positive and the negative leads, right, there's some mix of chemicals in here. Actually, I think I got a thumbnail. This was, yeah, shows what's the inner construction of a battery. Right. This is a classic example of a battery. Yeah, there's a potential difference, right? And if you can like get a wire connected to the positive negative lead, then that potential difference is going to induce some kind of current to flow, right? Now, voltage and current are different concepts with different units. I get to that too, but right, so sticking to batteries. Well, I got some batteries out, right? How about this boxy looking battery? How many volts is the big boxy looking battery? 9. There you go. Yeah, 9 volts, right? Right. Ooh, do you think I could stack up a bunch of these AA's to like, okay, so 1.5 volts. If I had another one, I could stack it right on top. It might be like 3 volts now, right? You had to like keep stacking them until I eventually reach 9 volts. How about the battery in your car? Turn on your car. How many volts? So like 12 volts, I think. About 12 volts, probably. Something like that. Right. I don't know. Maybe there's different kind of cars, but I was here 12 volts. Right. Like that. Okay. Right. All right, so more on these later. I got a whole like yeah, there's more posters related to these, but let's go on down this list here for now, right? Right. Also in your circuit, ideally you want some kind of resistance, some kind of resistor. And my classic go-to example is light bulbs. I have a bunch of Christmas lights here. They're all strung up different ways for different type examples I got lined up here, right? Right. So if you do not have any resistance across 2 leads of a battery, or I guess this is sort of the counterexample. What happens if you connect the positive directly to the negative? Has anybody ever done that? You guys ever taken a paper clip, or somebody earlier mentioned taking like a gum wrapper and just attach the positive directly to the negative? Right? What happens? Gets really hot really fast. Yeah, and it'll drain the battery really fast. Right? And it even has a specific name. It starts with an S. It's called a what circuit? Short. Maybe I should have said SH. I guess that should be its own letter too, right? Yeah, the short circuit, right? It shorts out, right? If you take a fancy electric appliance like your cell phone and drop it in a bucket of water, it shorts it out because now that that water is providing a path through electricity that's not through the traditional resistors, right? And so the thing shorts out. Okay, so good, right? Yeah, so you want some path for electricity flow from the positive to negative terminal of a battery, if you're popped in a battery, right, has to create a closed circuit all the way around, and ideally goes through a resistor, for example, this light bulb, so that it doesn't just short out and like drain the battery really fast, get really hot. Although I guess if you're like out camping and you had some batteries and you had to start a fire, you can use that to start a fire, right? Something like that. And the last one I got on this gold, it didn't print out very well on your thumbnails, but here you can see, you guys see the gold back and then the green back for the shading, right? So we're going to mostly just focus on these gold back ones today, right? Is power in watts. Now this one you guys have seen. You guys remember from last semester, right? Power in watts, right? Yeah, you guys had formulas with that, right? You guys remember it's like your rate of energy, joules per second. So in fact, this could just link back to straight kilograms, meters, and seconds. So some combination it takes for ingredients to create watts, right? Now, a lot of light bulbs are listed in watts. Like I got a 20-watt light bulb, right? That's kind of implied that you're plugging into like some voltage source, and then there's some resistor in that bulb, like in the filament in the bulb, such that paired up with some voltage source, it ultimately creates like 20 watts for going to shine, something like that. Okay, all right, guys, good. Okay. Oh, let's hook some of these up. So got 9-volt here. Got some lights. Let's see what this looks like. Right. Ooh, look at that, turns on. You guys see that? Okay. But I got 3 what's called in series here. I guess I'm jumping ahead a little bit. We'll get a little sneak peek to you guys see later today. Okay. What happens if I put them in a chain? Right. So you see how bright one is, right? There's one, how bright. Right. What if I put 2? Do you think it's same bright, brighter, or dimmer? Dimmer for each bulb? Dimmer, you guys think? Let's see. Ooh, it is a little bit dimmer, a little bit dimmer. What if I get 3 in a row? What's going to be even dimmer, do you guys think? Ooh, yeah, even dimmer. So they're all lighting up, not as much, right? And I do have another voltage source example here to pull this out. Right. Might possibly have you guys do a live version of this too, where there we go. Right. Now this extension cord is plugged into an outlet in the wall. Right. Now, who knows? Because we know what these batteries are. We've got 1.5 volts, we've got 9 volts. These are also called direct current DC, which I haven't quite talked about yet, but no. Right. But this wall socket is this alternating current, so it's like alternating back and forth. And does anybody know how many volts? How many volts in the wall? 120 volts, right? That's in North America. Do you guys know what it is over in Europe? It's like it's like twice as much. It's like 220, 220, 240, something like that, right? But yeah, in the States we're 120 volts, right? 120 volts, right? Do you want to go jam in anything directly in this wall socket? No, because you get big sparks of fire. It'd be bad. Don't do that, right? But here, I have a cell phone adapter. Now this will take 120 volts alternating current and step it down to just 5 volts direct current. Right? So plug this in. There's like a cell phone adapter. Right? Now here's 2 leads. Is it safe for me to touch these 2 leads? Can I touch these 2 leads? Is that okay? 5 volts direct current. Can I do that? Yeah. That I don't even feel anything. Right. That again, that's somewhere between these two. Like if I have these side by side, there's 1.5 volts, 5 volts potential difference, 9 volts potential difference. Right. This is like between the batteries. Right. Guys. Right. To show you guys this does light something up. Let's check out these guys right here. Let's do one. Ooh, look how bright. Ooh, look at that. Right, let's do all 3. Look, it's kind of dim. Interesting, right? I said, right? But yeah, the 5 volts there, 5 volts potential difference between these 2 leads. Right? Okay. All right, so I got this page out real fast. Let's hit these green ones. What's capacitance, inductance, magnetic field? I got all those right here in this Faraday flashlight. So this Faraday flashlight does not have a conventional battery in it. No, it's clear. You can kind of see. Right? There's no double A's, nothing like that. But do you guys see this magnet going back and forth past this coil of wires? Right. So this is like way ahead in this section, but this is electromagnetic induction. If I shake this magnet past this coil of wires, I'm transferring mechanical energy from my hand. It's turning into electrical energy is what it's creating, right? So what do we got going here? Got some magnet. It's really strong. It's probably a neodymium magnet, I'm guessing, right? That you can quantify how strong is the magnetic field in Tesla, which breaks down into these units, right? Inductance. This coil of wires right here is called an inductor. So if you run a wire, so that coil past that magnet, right, it'll induce an electric current, right? So inductance I can quantify in henries, which breaks down like this, right? That's like joules per amp squared. And then, I said this flashlight does not have a battery in it, but it does have a capacitor, right? Now, capacitor, think of it kind of like a battery, but it's not chemical energy storing. It's storing energy in electric fields. So electric fields, right? By the way, if you have some appliance like an old TV set or a microwave that's completely unplugged from the wall, is it safe to like take a screwdriver and just start like opening up a completely unplugged old TV set? No, not safe, because they might have capacitors in them that are still storing energy, right? And so you can turn this on. There you go. Yeah, turns on. Okay, just by shaking that back past that coil of wires. All right, so you guys good with the units coming up? Right. Right. I'm gonna come back and talk more about current and amps and voltage and volts. I'm not done talking about that yet, but move ahead here. Right. And so we got electric field. Right. So now this doesn't have to be 2 charges. I'm just showing 2 charges interacting, right? Maybe a positive and negative. Right? So you guys see how these field lines are conventionally drawn positive and negative, right? But if you just had 1 point charge, like, oh, hey, that purple balloon, right? Actually, that balloon would be negatively charged. Maybe I should focus on this. Something like that. Right. There's some electric field, and the closer you are to that charge, which you could quantify in some number of coulombs. So Q could be charge in coulombs. The stronger the field, and the further away you are, the weaker the field. In fact, it's an inverse square relationship, just like gravitational field was. Right? You guys remember that? Right? In fact, this kind of looks like gravitational field. Now it says electric field. Right? This K is a electrostatic constant, which is this number right here, electrostatic constant. Right? Q could be a point charge measured in coulombs, and D is your distance. And look at that, distance squared. So as you get further away, 1 over distance squared is electric field. Right? Kind of, this is analogous to like what's the gravitational field of the surface of Earth? Well, universal gravity constant times the mass of Earth divided by the radius of Earth squared. Right? So you guys see how it's analogous like that? Right. Right. So now, if you do have two interacting charges, you can get an electrostatic force. What's the strength of that force? Right? KQQ over d squared. K constant. Right? Nobody knows why it is what it is, but it's been measured to be that. Right? And then you got two charges and some distance between them. Inverse square law of distance. Boom. Looks a lot like G and M over R squared, doesn't it? Right? Now, when AP used to ask questions about this about 5 years ago, they would a question they like to ask once per exam was some version of how does this force compare to the gravitational force, right? Now, do you guys remember that, just to get some perspective on this, you guys remember universal gravity constant was like 10 to the negative 11, right? A bunch of units, right? This is like 10 to the 9, right? Guys, what's the difference between 10 to the negative 11 and 10 to the positive 9? Yeah, it's 10 to the power of 20, right? So it's like crazy. This is like 20 orders of magnitude stronger than gravity. Think of that way. Right? It's like when you drop your pen, it's like, yeah, gravity's pulling it down, but the molecules inside the paper are holding it up. Ooh, that's like 10 to the 20 times stronger. So it's not going to fall through the paper. All right, let's start looking at circuits. All right, real basic circuit. So classic example, flashlight. Right, I got the schematic and then kind of what the parts correspond to. If you see two parallel lines on a electricity circuit schematic, right? So one longer than the other. That's going to represent a voltage source, oftentimes a battery. Usually it's like a battery symbol right there. Okay? The long side is the positive lead, the short side is the negative lead. Right? As a side thought, I want to mention too, if you watch the electrons flowing on the wire, they do flow from negative to positive, but people didn't know that back in like Ben Franklin's day, for example. So they just flipped a coin, and as a convention, electric current is considered to be the flow of positive charge, which is like the opposite of the electrons physically flowing, which is kind of weird, but we just kind of stuck with it. So I don't know, it doesn't really matter mathematically though. Okay. And then this jaggedy looking symbol, we'll call that a resistor. And my classic go-to example could be a light bulb with a filament, something like that, right? If you see something like that, it could be an on-off switch. So if you close the switch, create a closed circuit, right? That's turning it on. If you open the circuit, that'd be turning it off, right? Is that closed open, right? Right. Yeah. So to make the circuit work, you need a wire that connects the positive to the negative terminal of your battery in this case. Right. It needs to go all the way around. Right. Create a closed circuit, and ideally also goes through some kind of resistor, because if it doesn't, it just shorts out. Okay. Right. You guys got all that? Right. Right. So I said I was going to come back and talk more about voltage and volts and current and amps and all that. Right. So when I first learned this myself back in high school, I was confused about these topics for a while. Like, what's the difference? What's voltage? What's current? Why is one thing doing one thing and doing right? Because I can't see it. It's all invisible, right? What's going on, right? Until like a bulb lights up or something, right? Then I was told this analogy, and this is what really made it click for me. So hopefully it does for you. Right? This helped, right? When you think voltage, think pressure, right? When you think of battery, which is some number of volts, right? Think pump, right? This is trying to like pump electricity through your circuit. So voltage, right? Like the more volts, the more pressure, things like that. Okay? And then electricity going through a wire, it's kind of like water going through a pipe. Okay, so voltage is kind of like pressure. Right? The current that ends up flowing through a wire, say you quantify this in amps, think of this being like a flow rate, like gallons per minute of water going through a pipe system, right? Cubic meters per second kind of deal. Right? And if you're looking at resistors, like there's a resistor, right? Think of it like a crimp in the pipe, maybe like reciprocal cross-sectional area, maybe something like that. Guys got it? And then you can put this all together with something called Ohm's law. Ohm's law, right? Tells you how much current flows given some battery with some voltage, some potential difference, right? Acting on some resistance, right? So do you guys see, like if you say you had like a 1 AA battery and then you popped in another right on top of it, so you like double the voltage. Because if you double the voltage, what happens to the current? Also doubles. Right? If that doubles, that doubles. Is it? If that triples, that triples. Is it? Right? And then what if you increase the resistance? What's going to happen to the current? Decreases. There's an inverse relationship. Well, that's kind of what I was shown before with so let's break this out again so you can kind of see this, right? Like if I only have one bulb that goes through, right? There's my entire circuit right there, and the bulbs that aren't lit up are not part of the circuit. Right? So let's just get this touch of this. There you go. There's only one that's actually lit up. Right, that's my entire circuit. It's what I'm pulling together there, right? But if I move this lead over so it gets all 3 bulbs in, that's effectively tripling their resistance. See how they're all 3 in a row? It's called in series. So 3 in a row. triple the resistance. If I triple the resistance, right, notice it's the same voltage. I've still got the same potential difference of 5 volts across these leads. But I just tripled the resistance, so I get 1/3 of the current, right? 1/3 of the current, and then them being dim. It's actually a power example. If you want to say like how bright is something, it's really just power, which I didn't quite put on this page, Ohm's law, but it's kind of an indication that goes hand in hand with that, right? Right. It's definitely less current, maybe 1/3 of the current. Right. So speaking of power, let's bring in power, and that's Joule's law. Joule's law tells you what's the power in watts, right? And here's 3 different perspectives on this, right? So start at the top here. You can go current times voltage, right? I times V, right? Right. Or combine this with Ohm's law. Let's do a substitution and kind of derive these other ones, right? You guys remember current is V over R, right? Let's take that and substitute it right there for that I. I'm going to substitute out the I and pop into V over R. Is that okay? Right. So would that be V times V divided by R? Right. Hey, that's this bottom one right here. V squared over R. Right. Or you could substitute out the V. You could do I times R. So sometimes Ohm's law is written that way. V equals IR. Okay. Substitute out that way. Be I times R. Hey, that's that one right there. I squared R. Okay. You guys see that? So, okay. So you guys go with power. Right? Again, that links back to powers and watts, and that's a concept you guys have known since last semester. Right. All right. Here's a Joule's law analogy. Again, electricity through a wire, water through a pipe. Right. What's what? Right. So this battery is kind of like a pump. Right. The voltage supplied by the battery, that's like pressure supplied by the pump. Right. Guys, what's the unit for pressure? Do pascals is one. There's other ways too, like psi and atmospheres, but you could do Pascal. And what's 1 Pascal break down to? 1 Newton per square meter, right? Force per unit area, something like that, right? Right. I've been telling you guys current, think flow rate, like gallons per minute. Let's swap that out for cubic meters per second, right? And then say I bet this light bulb here is like consuming energy at some rate. That's power, so it's I times V, right? So current times voltage, I times V, in terms of variables, is power. Right? P equals IV. There's Joule's law, one version of it, right? And then the analogous version is if you take this flow rate, cubic meter per second, multiplied by the pressure in the system, maybe we're trying to show this paddle wheel is going to hook up to a generator and create electricity on it or something, right? Right. That's some number of watts. So it checks out, right? Watts there, watts there. It really does work out too, like if you work through all the units, right? So it's a really good analogy too. Okay. You guys got that? All right. All right, let's start hooking up these resistors different ways. And we'll start with real simple. The simplest thing I could do is just in series, is just one after another. And this I already showed you guys earlier today. So here's my battery right here, or my potential difference, my 2 leads, right? And then go through 1 resistor and the 2nd resistor and 3rd resistor sequentially. See how the current has to go through all 3 resistors, one after another sequentially, right? Now, when you do that, from the point of view of your voltage source or your battery, it feels like it's effectively pushing against just some total resistance, right? And in a series situation, every time you add on another resistor in series, it's like it's increasing the resistance. So just very simply, you add up the resistors. So if it's like 1 ohm, 1 ohm, 1 ohm, together that'd be 3 ohms total. That's it. Okay, you guys get that? All right. Now, the other way you could wire up these bulbs, these resistors, is what's called in parallel, right? You guys see how this one's different, right? Like this is like rungs of a ladder. You guys see like rungs of a ladder? Right? That's not what we had before. Let me go back to before, right? Series, parallel, right? It's a little side by side. You guys see that's different, right? Like the series had to go through all, the current had to go through all 3 sequentially. It's not true for parallel. You guys see parallel, like, yeah, let's start with the voltage source. And I could go clockwise or counterclockwise. So I'm just gonna go, all right. No, just to remind you guys, right? The flow of the electric current is considered to be counterclockwise in this case. The physical electrons go clockwise. I'll just go clockwise. Wait, it doesn't matter, right? But some current's flowing around, and it's going to hit a junction. It has to split, right? And then here again, it's going to split. And it gets pushed through all 3 resistors simultaneously, right? You guys see that? Right? So some of the current cuts this way, and some goes this way, and some goes this way, right? Right. And from the point of view of the battery, your voltage source here, it says, well, how much total resistance am I pushing against? Okay? Now, in parallel, it turns out every time you add on another resistor, you're actually decreasing the total resistance. And the math behind that is exactly the same as the guys painting the fence. You see that? This is what we did for like Alan, Bob, and Carl painting the fence, right? You see it's the same thing, right? And every time you add on a new team member, it takes them less time to do the whole painting project, right? Oh, let me break out another analogy here. Let's do a traffic analogy. You guys want to do traffic? Right. Back to this voltage source, this battery. Let's say this is a parking garage. There's like 100 cars in the garage. Right? You guys got that? 100 cars in this parking garage? Right. And what they're going to do is they're going to drive out. They're all driving out this way. And they're going to drive around town and come back to the garage by the end of the day. Right? But they got 3 different ways they could go. Right? They could go across this resistor, or this resistor. Right? Right. Now, to kind of contrast this with the last example, in series, you have to go through all the resistors. Suppose the resistors represent stoplights. So all 100 cars have to go through all the stoplights, and it's the same current everywhere, right? All 100 cars. Right? But for this parallel setup, I bet this traffic is going to split, right? And if it's like one stoplight, it's going to split pretty close to a third each way, right? Right. We're kind of digging down into the circuit, thinking what's exactly going on, right? What about this though, guys? If there's suppose resistor A represents like 1 stoplight, resistor B is like 5 stoplights, and resistor Z is like 10 stoplights, right? Now, if you're a single car driving around, there's nothing in front of you, which path are you going to take? 1 stoplight, 5 stoplights, or 10 stoplights? Let's go 1 stoplight, right? It's called the path of least resistance, right? Guys, electricity wants to follow path of least resistance, right? Now you get all 100 cars going around, all driving around, right, trying to get back. Do you guys think that maybe most of the cars are going to go along 1 stoplight? But there's going to be a few cars that maybe go along to 5 stoplights, maybe like 1 or 2 cars to go along to 10 stoplights. You guys think something like that? So, okay, so it's going to be like a proportional type setup. You guys think, right? Okay. So what I'm kind of leading into is something called Kirchhoff's rules. We can like dig down into the circuit, figure out exactly what's going on with the voltage drops at each resistor, and how exactly does the current navigate and like split through some crazy circuit. Okay. So Kirchhoff's rules. You guys ready to go through Kirchhoff's rules? Okay. Now, really, if you open up a physics textbook and look up Kirchhoff's rules, then there's really only 2 rules. There's one called the loop rule and the junction rule, right? Now, you can kind of expand that, and there's some adjacent ideas, and I just put them all on one page, right? So, okay, maybe I'll start with the textbook. These 2 rules, I guess, they be defined, and then kind of branch out from there, right? So the loop rule says if you identify any loop within a circuit, the voltage drops have to sum to 0. So let's do an example, right? Because I see some loops here, right? So here's a complete loop. Suppose this is like let's bring up the 9-volt battery, right? So 9 volts, right? You guys ready to run some numbers? You guys got some paper in front of you? Got to throw some numbers at you guys, right? Suppose a 9-volt battery, right? So this is going to jump up 9 volts, pow, up 9 volts, right? And then it's going to, actually, I should turn the battery this way. There we go. Because here's the positive terminal, here's the negative terminal, because it lines up with my picture. Okay. Now, the voltage is going to drop down across this resistor and also down across this resistor, right? So that sums to 9 volts. So up 9 volts, down 9 volts, up 9 volts, down 9 volts. You guys get that? Okay. Now, if these resistors are the same, like 1 ohm and 1 ohm, you guys think it's going to drop down like 4.5 volts and then 4.5 volts? You guys think? Right. All right. Okay. You guys get that? Right. Okay, so that's like the loop rule there. There's more I want to say on that. Hold on to that idea because eventually head towards this, but this is a little bit more complicated. So, okay, great, guys. Right. But what about on here? Does this loop apply? By the way, I put the loop rule above this entire table because it applies to both series and parallel. So, right. But I see a loop right here. If this could be up 9 volts, down 9 volts here, this loop. Or what about the outside ring? Could this be up 9 volts and down 9 volts? You guys think? Ooh, okay, do right. Or what about this? Hey, here's a loop. Here's a little sneaky loop. You see it? Right. Now, one way you're going against the current, one way you're going with the current. Okay, so it'd be like 9 volts one way, 9 the other way. So it still zeroes out. Okay, you see that too? Okay. All right, so there you go. There's the loop rule. It applies to all these situations. Okay. And okay, since I'm going on a textbook, let's hit the junction rule. The junction rule says if you have a junction, right, here's a junction, the current's coming around, the current's going to split such that the 2 individual currents on these 2 new branches sum to the original current. So it's kind of a conservation of charge concept, right? So if suppose you have 9 amps, I'm going to switch over to amps. All right? Say I have 9 amps come this way, right? Drives around. Now, if these are the same resistance, say like 1 ohm and 1 ohm, do you guys think it's going to split exactly half and half? It's like 4.5 amps, 4.5 amps, right? But it still has to add up to 9. It comes back together. In fact, it makes 9 going back to the battery. That's the junction rule. Okay, so you guys go with those? Right. So yeah, here's your basic rules: loop rule, junction rule. Right. Right. Now, some other consequences that fall out of this are all the other rules I haven't mentioned yet. Let's go through those. Right. So for a series setup, right, you guys ready for this one right here? The series setup. Right. along a bunch of resistors in series, the current is the same everywhere, right? If you like the water analogy, it's the same gallons per minute everywhere. If you like the traffic analogy, it's the same 100 cars have to go through all these stoplights, right? But it's the same current in amps, same number of amps, even if these resistors are wildly different. Guys, well, let's see if you guys are following. If this resistor A is like 1 ohm and resistor B is like 99 ohms, is it the same number of amps going through both of those? Yes, it is. It's the same flow, right? Now, if you change out the resistors, it might change how much total current is set out from this battery to begin with, right? Well, say you have so many amps. It's the same number of amps all the way across. Okay, all right. Let me hit this one right here. Okay, remember that's just for series. Just for series, the current's the same everywhere. Right? Remember, in parallel, the current splits. Right? But speaking of parallel, what's going on with the voltage? And for parallel, the voltage drop is the same across both these resistors. Again, even if they're wildly different values of resistance, different number of ohms, right? So what if, no, how about say we've got like a 9-volt battery, right? So you guys back okay with this? We're back to this 9-volt battery, right? So I'm thinking in terms of volts now, 9-volt battery, right? Now let's say resistor A is like 1 ohm and resistor B is like 99 ohms. So got 1 ohm versus 99 ohms. Got a 9-volt battery. You guys think it's a 9-volt drop across A and also a 9-volt drop across B? Yeah, it's the same voltage drop, right? Because they be like the same pressure. Remember, I told you guys voltage is kind of like pressure, right? So we pumped up the pressure so much, the voltage so much, it drops so much across each one of those. Okay, right. Did I light up all three in parallel already? Did I guys do that for you guys? Here, let's do it real fast. Right. So say you threw on one more, right? Something like this, right? These are all going to light up. Ooh, I don't know why it's looking so dim, right? But should be brighter than that. Anyway, right? You see how like they're the same brightness. Right? Even if I switch these out with, like, if I change out these bulbs, maybe they'd be different brightnesses, but they got the same 9 volts across them. Every single one of these has 9 volts going across it. Okay, right? Or if I swap out for the cell phone charger, right? Let's have 5 volts going across each one. Okay, I don't know. I think this battery's like broken or something, or maybe it's getting drained, right? But I bet that's 5 volts going across every single one of those, right? Because they're all tied together like that. You see that? All tied together. Right, so it's like a parallel setup. Okay. Right. You guys good so far? Because right, the only ones I haven't quite mentioned yet are these fraction-looking ones. Right, you guys ready for the fractions? Right. So, right. So, you guys ready for some numbers? You guys got notes out? Hold it. Right, now, how does the voltage drop? Let's just go to series. How does the voltage drop across each one of these resistors? This rule here says it's proportional to each resistor. Right. So if they're the same resistors, it's going to go halfway and halfway. Right. But what if it's like a 1 ohm and 2 ohms? You guys get that? Resistor A could be 1 ohm, resistor B could be 2 ohms. Right. This fraction says that 1/3 of the voltage drop, 1 out of 3, happens across the 1 ohm guy, and 2/3 of the voltage drop, 2 out of 3, happens across the 2 ohm guy. So bring in the 9-volt battery, got 9 volts here. See if you guys are following. 9 volts. Here's 1 ohm, here's 2 ohms. 9 volts. How many volts drop across the 1 ohm? 3. How many volts drop across the 2 ohms? 6. And what's 3 plus 6? 9, which is consistent with the loop rule. See how it all comes together? Okay, right? But remember, the current's the same everywhere. It's the same number of amps. If you count for amps, it's the same current goes through. Okay, but voltage drop is proportional to each resistor. Okay, right. How about the parallel setup? Right, and now this very last fraction takes a little bit deeper thinking. It makes sense, but you have to think about it a little bit deeper. This says, how does the current split? The current through branch A is proportional not to resistor A, but to the other resistor, resistor B. You see that? See how there's a little subscript swap right here, right? So, for example, say I got 9 amps coming around. You guys okay with 9 amps coming around? That's not necessarily this battery though. Right? 9 amps, right? And then it comes up to, let's say resistor A is 1 ohm, resistor B is 2 ohms, right? Hey guys, if there's like 1 traffic light and 2 traffic lights, which way is most of the traffic going to go? Through the 1 traffic light. I bet 2/3 of it goes through 1 traffic light. I bet only 1/3 of the traffic goes through the 2 traffic lights. Is it? As it's going around trying to drive back to the parking garage, right? That's exactly what this says. The across the 1 ohm guy, there's 2/3 of the traffic goes that way, in terms of amps. Right, guys, good? Again, all this electricity stuff you can apply to if you're a traffic engineer, if you're a pipe system engineer, but a lot of other systems like this, right? All applicable, right? Right. Kirchhoff table. If you set up some circuit, you can keep track of like what's each resistor, what's the voltage drop, what's the current each location, what's the power in watts, right? I've got some examples of that. So, good. We got a good amount of time here. I'm going to show you some examples, right? I got this waterfall analogy. So here's my schematic, right? So voltage source like a battery. Here's 3 resistors. Now this is all series. You guys see it's all straight series, right? What would that mean like if I turn this into like a pump and water flowing situation, right? So this battery is like a pump. It's gonna pump it up like this clip, right? And I got, look, 3 waterfalls all in succession, like sequentially, one after another, right? Do you guys see the voltage drop could be different for each one? That's like waterfall heights. That could be different, right? Like if these different resistors, that's okay, right? But I could have different resistors in different waterfall heights, but you guys see it's like the same gallons per minute everywhere? That's like the same current everywhere. Okay, okay. And I threw some numbers on here too. I think tomorrow I might give you guys a worksheet type page that has some circuits on it and have you guys fill out these tables. On these tables, I'll give you a few starter numbers. You guys see some gold boxes? You guys see 4 gold boxes? Right. Those are givens. So I gave you resistor A, B, and C and ohms. How many ohms the resistance is each resistor, right? And I also gave you, in this case, a 12-volt battery. You guys see a 12-volt battery, right? Now, once you know that, everything else in this table becomes determinable, right? So let's start with what's the equivalent resistance for the entire circuit, right? Well, can I just add these 3 resistors together because they're in series? Can I just do that? What's 1 plus 2 plus 3? 6, right? That's where this comes from. This says resistance equivalent is, and the answer would be 6 because they're in series. You just add them up. Okay, good so far. Right, right. Now, voltage. Right. This one's a little tricky to figure out, right? For this particular, sometimes, right? I guess it's kind of like a Sudoku puzzle, right? Once you know some starting values, everything else becomes determinable, right? But I'm thinking more like this one right here. So I got a series set up, try to figure out what's the voltage across each one. It's going to be proportional to each one, right? Well, out of 6 total ohms, 1 ohm is just resistor A. Is that like 1/6 of the total resistance, right? And since I have a 12-volt battery, guys, what's 1/6 of 12? 2. So I'm saying there's a 2-volt drop across that resistor, right? And then it follows 4 and 6 for the other one. Okay, guys, hey guys, what's 2 plus 4 plus 6? Adds up to 12. That satisfies the loop rule. That's it. Right. Now, you guys remember Ohm's law? Do you guys see a poster up here that says Ohm's law, I equals V over R? Let me find that for, okay, while you guys are following that. Find that, right? I'm thinking about this right here. If you're watching this video at home, right? We're about to navigate this. You guys ready to navigate this, right? So how much current is actually flowing, right? Well, guys, what's 2 volts acting on 1 ohm? 2 amps. What's 4 on 2? 2. What's 6 on 3? 2, right? In fact, it had to be, right? Because they're all in series. They better all be at the same current. And if they weren't, then something's messed up, right? And then there's 2 amps going through the battery. Finally, let's do Joule's law. Right. Oh, I got 3 different perspectives on that. Right. Well, let's try them out. Right. So you could do I times V, current times voltage. What's 2 times 2? 4. The power in watts is 4 watts. Right. Or you could go V squared over R. What's 2 squared divided by 1? 4. Or you could go I squared times R. 2 squared times 1 is also 4. Right. Right. Try it for the other ones. Right. Now, what's the total power demanded? Guys, what's 4 watts plus 8 watts plus 12 watts? 24 watts. And it turns out, if you do Joule's law at the point of the battery, there's also 24 watts supplied. So like supply is meeting demand kind of thing, right? And then at that point, you think, okay, well, that looks a pretty good table. Okay, here's good. All right, let's look at a parallel setup. Here's parallel, right? Now this one, you know the voltage drops are all going to be the same because they're all in parallel, even if the resistors are different. So same as before, I set you guys up with, I gave you guys 3 resistors. So those are gold boxes. I also gave you a 12-volt battery. Now this one, how about this? Let's do a fence painting analogy. Suppose there's 3 friends painting a fence. This guy would take him 2 hours, this guy 3 hours, and this guy 6 hours, right? How long do you think it would take them 3-man job to do it all together? Can you do 1 over 3, or sorry, 1 over 2 plus 1 over 3 plus 1 over 6, and then take the reciprocal, right? And just to, I know we've only got like a couple minutes here, right? Do you think you get 1 hour to finish the job? In this case, there's 1 ohm resistance. This battery right here feels like it's pushing against 1 ohm, right? Now the current leaves the battery and then it splits 3 ways, right? oh, look, it's the same voltage drop across every single one, which in this case matches the battery, right? It's 12 volts across every single one, right? And then if you dig into it, say, now the current flows differently, and here's the power outputs, something like that. Right, you guys good? You guys good? Right. And let's do so the last few things here today is what if you have some hybrid system, right? Something that's not exactly series, that's not exactly parallel, right? And there's a process for figuring this out, which is if you want to figure out what's the total equivalent resistance, what you do is this: you start at the point of the battery, you fly over to the opposite side of the circuit, and you work your way back and find equivalent circuits. Right? So these two are in parallel. So you do product over sum, like Peyton and Fence. Write that number down. Then bring in this guy here, resistor C. That's in series, so I just add him. And then work back towards, okay, now I got resistor D in parallel again, so do another product over sum, right? And in this case, if you run these numbers, it comes out to 2 ohms if you do it correctly. Okay? And just to, let's see if I got, okay, this isn't exactly what you're seeing, but this is also a hybrid setup. Do you guys see, let me put this up before the bell rings, right? I have 2 in parallel on my right hand, and then that's in series with 1 on my left hand. What's this going to look like if I pick this up? Do you guys see all the electricity goes through the bright one, but then by the time it gets to the 2 dim ones, the electric current has to split. That's probably why they're dim, right? You see it? All right. So I think it's a good pause point today. And then, yeah, we'll do more electricity next couple days. All right. You guys have a good afternoon.